Hey, Honors Physics. This is yet another video lesson about circuits for you. I wanted to start with this recap from last week about series and parallel objects in a circuit with resistors in particular. Two objects are defined as being in series with each other if there is only one pathway, basically. If they come one after another on a single pathway, then we say that they're in series. A simple example of that would be this little section here. I have two resistors. You can see that there's only one way to go if you want to get from the left side to the right side. And you just go through both of the resistors. If you want to know the total resistance for a series combination of resistors, you can just add the R values together. Objects that are in series with each other will always have the same amount of current, but in general, they're going to have different voltages. Now, if the resistors happen to be identical, then they'll have the same voltage. But in general, they're going to be different because each voltage for each resistor would be calculated by using V equals IR. They have to have the same current I. So if they have different R values, you'll get a different voltage. And then in contrast, we have a parallel combination. Parallel arrangements provide multiple pathways, alternate paths. So that looks more like this. If you start on the left and you want to get to the right, you can either go up or you can go down. There's no way for you to travel through both of them to get from one side to the other. You pick. If you want to know the total amount of resistance when there are resistors in parallel, you have to do that weird reciprocal addition. So you take 1 over each R value and get the sum of the reciprocals, and then you take the reciprocal again to get the total. When objects in a circuit are in parallel, they in general are going to have different currents flowing through them, but they will have the same voltage. So similar to what I was saying for the series combinations, if the resistors happen to be identical, then you'll get the same current. If the top path is 100 ohms, the bottom path is also 100 ohms, then the current is just going to split 50-50 between them. But if one of the paths is easier than the other, then more of the current is going to take the easy path. And you can find the amount of current that goes through any individual resistor, again using V equals IR. You're going to know the V because they have to have the same V between these two dots. And if you know the resistance R, then you can calculate the current that each one gets. All right, so let's look at an example circuit. I'm going to run through this pretty quick because this is similar to what you were doing last week. You can solve a circuit like this by basically using V equals IR over and over again. You can apply it to any single resistor or to any section that contains only resistors, as long as you've figured out what the equivalent resistance is for that section. So for example, this particular circuit, if you find the total resistance for the whole thing, it's 18 ohms. The parallel part is 1 over 10 plus 1 over 40, and then you take the reciprocal of that. That gives you 8. And that parallel section is in series with this 10. So it gives you a total resistance of 18. So once you've determined that, you could use V equals IR to find how much current is coming out of the battery, right? You can imagine the whole circuit is just the battery and then a single resistor that's 18 ohms. So you do 9 volts over 18 ohms, you get half an amp of current. You could determine the potential difference or the voltage for the first resistor once you know the current. V equals IR. I know the current is half an amp. I know the resistance is 10 ohms. So the potential difference or voltage for that resistor is 5 volts. I could find the voltage for the parallel section the same way. As long as I'm pretending that the parallel section is a single 8 ohm resistor, V equals IR. The current that flows through that section is half an amp. The resistance of that section is 8 ohms, so I get 4 volts. And then once I know the voltage of that parallel section, I can find the current for each individual resistor. There's got to be 4 volts here, and the resistance is 10, so the current is 0.4. There's also 4 volts here. 4 volts over 40 ohms is 0.1 amps. Now I can show you all of that in the simulation where I drew it. Battery's already labeled as 9 volts, but I'll measure that first. If I measure the voltage for the 10 ohm resistor, I get 5. Something interesting here is that it reads -5. That's because the black probe is the reference point for the meter. What it's telling me is that the red probe is 5 volts lower than the black probe. If I reverse them, it would turn positive. But this minus sign is actually meaningful. And we'll get back to that a little bit later. If I put the probes in the parallel section, I should get something with magnitude 4. So that verifies all of the voltage calculations. Current here, half an amp. Current through the resistor, half an amp. If I take this left branch, 0.4 amps, and I get that same reading the whole way along the branch. On the right branch, 0.1 amps. And then after the intersection, it'll go back to 0.5. So there's 2 interesting things about those results. First of all, the voltages for this resistor and the parallel section, they were 5 and 4, and that makes the same 9 volts that I started with for the battery. And the currents in the parallel section were 0.4 and 0.1, and if you add that together, you get the same 0.5 that I had for in the single path sections. Both of those phenomena will occur in any circuit that you analyze carefully. And so those ideas are formalized into 2 rules, which are referred to as Kirchhoff's Rules, named after the person who originally stated them clearly. So the first rule is about volts. The potential differences that you encounter if you follow any complete loop through the circuit have to add up to 0. When you're doing this, it's important that some of the potential differences are going to be negative. And I drew attention to that in the simulation there briefly. So you can choose any path that you want in the circuit. I'm going to show you a few examples in a second. But your path has to form a complete loop, so you return to where you started. And if you're going to follow some path in the circuit, that means you have to choose a direction that you're going to move as well. So if you go through a battery, I'm saying forwards, quote unquote, forwards here. So if you go from the negative end of the battery to the positive end of the battery, its potential difference is going to be positive in that case. That's because the positive end has a higher potential. So if you go that way, your potential is going up. So that's a positive voltage. If you go the other way through the battery as you're tracing your path, then you would have to count its voltage as negative. Resistors also can be positive or negative, depending on which way you go. But here it depends on the direction of the current relative to the direction that you are traveling as you imagine yourself moving through the circuit. So if you go in the same direction as the current, the potential difference is negative. And that goes back to electrostatics, the idea of electric potential in the first place. You may remember that electric fields point, metaphorically speaking, downhill. If you think of potential as being like a height or an altitude, electric field points downhill, and current also flows downhill, just like the current in a stream or a river flows downhill. So if you're going with the current, in this case the current goes clockwise, goes to the right out of the battery through this resistor. If you go through the resistor with the current, you're going downhill. So that's a negative voltage or a negative potential difference. If you are moving against the current, like a salmon, then that is a positive potential difference because you're going uphill. This law basically is like the conservation of energy. It says that your potential energy changes every time you go through an object, but if you return to where you started, you should have the same potential energy as when you began. So here's a couple examples. If I use this path, I've drawn a green arrow that traces a complete loop starting in the battery, goes around. The values I would fill in when writing this loop would be 0. The battery is +9 because I'm going forwards through it from the negative to the positive. Then I pass through this resistor in the direction of the current. I remember that the voltage was 5, so I used a 5, -5. And then I go through this resistor, and the voltage for that section of the circuit was 4. So -4. And indeed, 9 minus 5 minus 4 is 0. Here's another loop. Your loop does not have to include any batteries. So I'm just going in this little section on the right. I go through 2 resistors, no battery. In the first resistor, I'm going in the same direction as the current. I'm going down through that resistor. That's the way the current goes. So I'm going downhill. So it would be -4. And then in the second part of the loop, I'm going back uphill. So I have to use a plus sign on that resistor. And astoundingly, 0 equals -4 plus 4. And in this circuit, there's a third possible loop I could do if I just trace the outside. So I'm again going clockwise. I could choose to go counterclockwise, but I wrote this one out as clockwise again. So 9 for the battery, -5 for this resistor, -4 for this resistor. And that takes me back to where I started. If I went counterclockwise on any of these 3 loops, if you change the clockwise versus counterclockwise direction, all it does is multiply the whole equation by -1. So like if I was going the other way around for this outer loop, I'll start here in the middle of the top. I'm going backwards through the battery, so it would be -9. Then I'm going uphill through this resistor, so it would be +4. Uphill through this resistor, +5. So it looks just like the equation I wrote, except all the signs are flipped. So the direction you choose does not matter, as long as you know the current direction so that you can put proper signs on your resistor terms. Okay, the other rule is about current. So we had a rule about volts. We also have a rule about current. This rule says that the currents entering or leaving any section of the circuit, and usually we focus just on little intersections, junctions, those currents have to also add up to 0. So you could write it as the sum of all currents equals 0, or you could say like currents coming in has to equal the currents going out. Same thing. If you're going to use this sigma, the summation notation version, you have to put plus and minus signs on the currents. doesn't matter which convention you choose, but like say everything coming in is positive and everything going out is negative, or vice versa. But you have to keep track of that. This rule is basically about the conservation of charge. And that's something that we talked about very briefly at the beginning of electrostatics. But you saw a lot of questions about, like, I have two charged spheres and you touch them, and what are the charges afterwards? Same idea. All right. So examples for that one. If I choose this top junction, there's a current coming in from the 10 ohm resistor, and I know that that current was 0.5 amps. So that's my first term here, plus 0.5. And then I have two currents coming out. There's some current going down this way, and that amount was 0.4 amps. I put a minus sign on it. And then there was 0.1 amps going out this way. So I chose to make coming in positive and going out negative. So this is the summation notation version, or if you just want to say in equals out, the incoming current is 0.5, the outgoing currents are 0.1 and 0.4. And I think it's pretty clear that these are actually the same equation. So it doesn't matter which way you think about doing it. I can do the same sort of thing for the bottom junction. I have two currents coming in. That's the 0.4 and the 0.1. And I have one current going out, which is the 0.5. So again, you could write it in either style. They have the same meaning. Okay, so here's a couple examples. So I revealed the answers too soon. Here's a couple examples. In this left-hand circuit, I have some of the potential differences labeled, just in terms of their magnitudes, but I have some potential differences labeled, and I want to find the other ones. So, for example, the potential difference for the voltage for resistor A here. If you think about drawing a loop on the left side of the circuit, I know that I get a plus 24 from the battery, and then I would drop my potential by some amount, and then I would drop my potential by 16 volts, and that takes me back to where I started. So basically A plus 16, these two, they have to add up to 24. So that means resistor A must be 8 volts. And then for resistor B, you could either do another loop, you could go around the outside, you could do a loop just on the right side, or you can also apply the idea that things in parallel have to have the same voltage. This pair of resistors is in parallel with this one. So if there's 16 volts on this branch, there has to be 16 volts across this branch also. 10 of them are here, so that means B has got to be 6. So 8 and 6 are those unknown voltages. For currents, similarly, you can either apply Kirchhoff's rule about junctions, or you can apply the idea that objects which are in series have to have the same current as each other. So, for example, if I want to know current A, if I sort of backtrack around the battery, you'll notice that I already have the current labeled as 12 here. So this wire and the battery are in series with this resistor. There's no intersections between them, if you go clockwise at least. So that means A has to be 12 amps. There's nowhere else for this current to go. So all of that current arrives here. That's 12. And then I can see that 9 amps went to the right. So that means that B has to be 3. It's got to be 3 amps for B. And that's an application of the junction rule. 12 amps in, 12 amps out, 9 and 3. All right, Here's a slightly more complicated voltage case. You have to use a little bit of knowledge about equivalent resistances for this one. So there's only a single volt amount labeled, but we have this information that the resistors are all identical. That's going to be useful. So first one that you can figure out in this, you kind of have to start with resistor C. And resistor C has to be 3 volts because it's in parallel with something that's already labeled as 3 volts. Objects in parallel have the same voltage. Okay, so C is 3 volts. Now what I've got here is a pair of identical resistors. So if I just call that resistance R, I don't know what it actually is. I'm just going to call it R. The equivalent resistance of that parallel piece has to be half R, because they're in parallel, so you add by reciprocals. I'd have 1 over R plus 1 over R, that's 2 over R, and then you take the reciprocal, which becomes R over 2. So the resistance of this piece is R over 2, but I know the resistance of this piece is R. So B has twice as much resistance as this section does, and since they're in series with each other, B is in series with this equivalent imaginary resistor of R over 2. That means they have the same amount of current flowing through them, and that means that the voltage for resistor B has to be twice as much. Same current, twice as much resistance means twice as many volts. So B has to be 6 volts. And then once I know those, I can do a loop around the whole circuit to find the battery's voltage. If that's 6 and that's 3, that means the battery must have been providing 9. And here is a current problem. This time the resistors are varied, but we are given information about them. So these 3 are identical to each other, and I've named that R0. This one is also R0, but this one is 3 times as much. This one is 2 times as much. And we're given a single current. This top resistor, it has 1.2 amps flowing through it. So this time I would start with that parallel section of 3. Since I know the resistors are identical and they're in parallel, they're going to get the same amount of current. This one has 1.2 amps, and the other 2 also have to have 1.2 amps. Since those 3 pathways are equally difficult for the current to flow through, it's going to split equally among them. So they're all 1.2 amps. All right, so when those 3 currents come back together again at this junction here and flow around, they combine to make 3.6 amps. And so this resistor is labeled with a resistance value, but I don't actually need to know its resistance. There's only one path here, so all of that current has to come together, and 3.6 amps flow through this resistor. But when that current reaches the next intersection, it's going to split. This time it will not split evenly, because the top path is 3 times harder to flow through. The bottom path is easy in comparison. And everything with circuits works in simple proportions. So I should have 3 times more current in the bottom than I do in the top. So that means that 1/4 of the total current goes through the top, 3/4 of the current goes through the bottom. That's the only way for the bottom to be 3 times bigger than the top while still adding up to 3.6. So those answers become 2.7 and 0.9. Okay, so those examples were kind of like puzzles, as I said. You didn't have to do any complicated math. You had to sort of apply a couple of different concepts, but the math was pretty straightforward. In principle, Kirchhoff problems can get very complicated, and so I'm going to describe the setup of one of those, but I want to tell you up front that I'm not going to give you any super complicated Kirchhoff problems because they are extremely tedious algebraically. So I have this circuit. If I wanted to, I don't have any numbers in this example because I want to show you how the equations are set up. But if this were a real problem, I would give you like a subset of the numbers and ask you to find the other ones. And it involves setting up a system of equations because there are multiple loops that you can write formulas for. There are multiple junctions you can write formulas for. And then you have this big list of equations, and you'd have to substitute them into each other or like make a matrix or something that nobody really wants to do. So I have all the resistances labeled and the EMFs of the two batteries. If the currents for the problem are not already indicated, you need to start by indicating currents. So the layout of this circuit has three total pathways or branches. There's this middle section, and then there's the left section and the right section. Basically every path between junctions, or if you like graph theory and math, every edge between nodes. So there's three edges in this diagram, or three branches, whatever you want to call it. So you have to give each one of them its own current. And I've just named them I1, I2, I3. I matched the subscripts. So resistor 1 is where current 1 flows. Resistor 2 is where current 2 flows, and so on. And you have to assign a direction for each current also. You're not necessarily going to know the directions for the currents ahead of time, so just make a guess. I can see that both of the batteries are facing up, so I chose to make the currents go up. And then when the currents merge here, they would flow down together and then split again. But potentially, like if battery A is 1,000 volts and battery B is only 1 volt or something silly like that, then I might have guessed incorrectly for these directions. But it's not a big deal. The worst thing that can happen, assuming you don't make any algebra errors, is that one of your answers at the end of the problem has a minus sign on it. It's not going to change the magnitudes. You're just going to get a minus sign, and from that you can tell, oh, I guessed incorrectly. So there's no need to stress out about it. So I'm going to start by writing my junctions. The top junction has current 1 and current 3 both coming in. That's up here. 1 and 3 come in, 2 goes out. So plus I1, plus I3, minus I2. And the bottom junction is the opposite. Plus I2, minus I1, minus I3. And notice these two equations say exactly the same thing. If you just multiply them by -1, you get the other one. So what that tells us, and this happens all the time, is that you don't actually have to write every single junction. At least one of them will be redundant. There's only 2 junctions to choose from in this problem, so that means you definitely only have to write one junction equation. In a really complicated circuit that has like 5 junctions or something, you're not necessarily going to know going in how many of them are independent of each other or which ones are independent. So you might still need to write them all when you're getting started. And then for the loops, I have 3 loops that I can choose from. There's the outer, the left side, and the right side. I'm going to go clockwise on all 3 of them, but again, you can choose whatever direction you want. So for the outer loop, 0 equals I'm starting in the lower left corner here. So if I go clockwise, I pass through battery A. So I wrote plus EMF A. Then I go through this resistor. I'm passing through this resistor in the same direction as the current. So that means I have to subtract the potential difference for this resistor. And the potential difference for any resistor is I times R. The I here is I1, the R is R1. So I wrote minus I1 R1. As I continue that loop along the outside, the next thing I encounter is resistor 3, and I'm going against the current that I drew for resistor 3. So I have to use a plus sign on this term. And then IR. The I there is I3, the R there is R3. After that resistor, I pass through the battery, and I'm going backwards through the battery. So I put a minus sign on it, and then EMF B. The left side loop, I'm going to start again in the same place. So plus EMF A minus I1 R1. But then I go this direction, moving in the same direction as current I2. So the last term is minus I2 R2. And then for the right side loop, I will again start in the lower left corner of the loop, but it doesn't really matter. Since I'm going to go clockwise, that means I'm going uphill in the first section. So plus I2 R2. Then I hit resistor 3, again going backwards. Oh, I have a typo. That should be a plus. I'm not going to re-record the whole video just to fix that. That should be a plus. So plus I3 R3, and then I go backwards through the battery. So minus EMF B. Just as with the junction equations, if you write out every single loop, at least one of them will be redundant. They're not all independent equations. In this particular case, if you subtract the first two equations, you'll get the third one. So that means they're not all independent of each other. But just like I said with the junctions, you're not really going to know going in which particular loops you need. In this case, where there's only 3 possible loops to choose from, you're just going to need to write 2 of them. But if you had a more complicated circuit with like 5 or 6 loops, in practice, you're probably just going to write all 6 of them and then see what you can do with them once you've got them. So, as I said, in principle, once you have this system of equations, you could use some algebraic technique to combine them all and solve for whatever the unknown quantities are. Some of these numbers would have to be given to you. In this particular circuit, I have 3 independent equations, right? Because only one of the junctions was independent, and then 2 of the loops were independent. So with 3 independent equations, I could solve for 3 unknown quantities. So for example, if all of the resistors and batteries were given, you could find the 3 currents. You could determine all 3 current values. Or if any other combination was given, as long as there were only 3 unknown quantities, you could figure out what they were, regardless of which quantities they were. But again, no one really wants to do that. Solving systems, especially systems with more than 2 equations, is not pleasant. It's just really tedious. That's the kind of thing that's really better to have a computer do than trying to do it by hand. So I'm not going to make you do that. You'll see like one simple example of this in the classwork, I think. Nothing nearly as complicated as this one. And that is all I've got. So that's the whole lesson. Most of your classwork is going to be similar to the puzzles. So kind of like this one, where you have to do a little bit of application of like equivalent resistance rules or proportionalities, like similar to what I did here. Like if I know this resistance and voltage and I know this resistance, I can determine that that voltage has to be twice as much. There's going to be some reasoning like that in the classwork, along with usage of the Kirchhoff rules themselves. And that is all I've got to say.